By applying Kirchhoff's voltage law on the base emitter biasing circuit, we can derive an equation for the base current. When applying Kirchhoff's voltage law, we can either select a clockwise closed path or an anti-clockwise closed path. Pick any point as a starting point of the closed path. For example, the positive terminal of the supply VBB. From here to here, there's a voltage drop because the base current is flowing in this direction. As current always flows from high potential to low potential. From here to here, there is a voltage drop across RB. According to Ohm's law, this voltage drop is equal to IB times RB. As current is flowing from B to E, there is a forward bias voltage drop across the base emitter PN junction. So far, we have two voltage drops in the path, VRB and VBE. Let's continue. From the emitter going back to the positive terminal of VBB, there is a voltage rise of VBB volts. Some of you might ask, why not a voltage drop? The reason is simple. In the symbol of a DC voltage supply, the side with a short line is the negative terminal, and the side with a long line is the positive terminal. Going from the negative terminal to the positive terminal, there must be a voltage rise equal to the EMF of the DC supply. Kirchhoff's voltage law states that the sum of all the voltage rises in a single closed path in the circuit is equal to the sum of all the voltage drops in that closed path. Hence, this equation is written. VBB is the voltage rise, and these two terms are the voltage drops. Rearranging the equation, we obtain this equation for the base current. In this circuit, the emitter is connected to both the base emitter biasing circuit and the collector emitter biasing circuit. Therefore, this circuit can be referred as common emitter biasing circuit. As the emitter is taken as the reference ground, the voltage at this point is VBB, and the voltage at this point is VBE. This IB equation can be viewed as the direct result of applying Ohm's law. That is, the current flowing through a resistor is equal to the voltage difference across the resistor divided by the resistance. How about the collector current equation at this side? Similarly, we apply Kirchhoff's voltage law to derive it. From the positive terminal of the supply VCC to the collector of the transistor, there is a voltage drop equal to IC times RC. As the current is flowing from the collector to the emitter, there is a voltage drop from the collector to the emitter. This voltage drop is labeled as VCE. Let's continue. From the emitter going back to the positive terminal of VCC, there is a voltage rise of VCC volts. According to Kirchhoff's voltage law, the sum of all the voltage rises in this closed path is equal to the sum of all the voltage drops in this path. Therefore, VCC is equal to IC times RC plus VCE. Rearranging the equation, we can easily obtain these collector current equations. Similar to the base current equation, the collector current equation can also be viewed as the direct result of applying Ohm's law. As the emitter is taken as the reference ground, the voltage at this point is equal to VCC, and the voltage at this point is equal to VCE. The collector current is equal to the voltage difference across RC divided by the resistance of RC. Let's summarize the current equations of this common emitter circuit. By applying Kirchhoff's voltage law, we derive the base current equation and the collector current equation. By applying Kirchhoff's current law, we have the third equation. The emitter current is equal to the sum of the base current and the collector current.